Hi, so this is going to be my first video on special relativity and the derivation and explanation on many of its concepts and ideas. So I've seen a lot of derivations on YouTube and other sites that will explain some concepts from the ideas of either concepts that have been introduced later on or equations that seem to appear out of nowhere. And the point of these videos is to explain special relativity from the beginning all the way to, actually the first video I think I'm going to make is to E equals mc squared and time dilation, length contraction, and other areas of special relativity. So for these videos, the only thing that you really need to know, at least, well, for this video, is the simple idea that in a triangle, if A, B, and C, a squared plus b squared equals c squared. Easy enough, so know that. Pythagorean theorem. And also that a distance traveled equals velocity times a change in time. So, if I'm watching a truck move at a certain velocity, and I calculate the time that it's traveling, if I multiply the time by the continuous velocity, I'm going to get the distance that it traveled. So, special relativity. Well, a lot of special relativity is based on the concept that the speed of light is absolute in all reference frames. And what a reference frame is it's a frame of reference, so it can be a coordinate system or in this case it'll be a state of motion by which you observe the events around you. For instance, a good concept is that if you were traveling in deep space in a completely closed off spacecraft with no windows, nothing, at a constant velocity, didn't pass by any gravitational fields or forces, you would have absolutely no idea that you were moving. There would be no way to test that out. Now, what different reference frames mean is, say there was a completely blank space and you were in this spaceship and there was another spaceship that you saw moving away from you like this. There would be no way to tell whether this spaceship moving away from you was actually moving like this, or the spaceship was stationary and you were moving back like this, or you're both moving a little bit. There'd be no real way to tell. It would just look relative to yourself, as if you were standing still and the other object was moving. The other object could be standing still and you could be moving very well, you just wouldn't know the difference. And so those two frames of reference would be different reference frames. And in this case, they'll be that state of motion will be the velocity of the object for these explanations. It could very well be, and later on in one of my other videos, it will be different coordinate systems by which lengths and positions are measured. So the speed of light, like I said, is represented as c and is absolute for all reference frames. Normally, in classical physics, if I was driving a car, or say, if I was driving a car and you were standing on the side of the sidewalk and stationary, okay? And, say it wasn't a car, say I was on the back of a truck that was moving at a certain velocity of v, and I had a tennis ball in my hand and I was standing on the back of the truck, and I threw the tennis ball. You, standing on the sidewalk, would see the velocity of the tennis ball being the velocity that I threw it in reference to the truck, plus the velocity of the truck. So you'd see the tennis ball moving faster than the truck because it would be the velocity of the tennis ball plus the velocity of the truck. Likewise, if the truck was moving and I threw the tennis ball backwards, you would see the velocity of the tennis ball being the velocity of the truck minus the velocity of the tennis ball that I threw in reference to the truck. However, with the speed of light, that wouldn't be the case. If I was driving and I shown speed of light, shown a flashlight, it would travel at the speed of light. You wouldn't see the speed of light, the speed of that light beam, as the speed of the truck plus the speed of light, because that's impossible, because the speed of light is the absolute speed. Likewise, if I shone the light backwards, the speed of that beam would appear to be wouldn't appear to be the speed of the truck minus the speed of the light. It would just be the speed of the light. It is absolute. That's just a scientific law. Okay, so that's a little bit about special relativity. Anyway, what I'm going to start with is an idea called a time clock. This is going to lead up to time dilation, which basically says that for objects in a, if you have two reference frames, an observer in one reference frame would see that time in the other reference frame would be going by slower than in their own reference frame. And it's going to be proven through a concept of a time clock. And let me show you what a time clock is. I'm just going to draw this, and this is going to be a time clock with a little device over here. And how it works is it shoots a beam of light up, and this is a mirror, and it bounces off the mirror and comes right back down. It's kind of like ticks on a clock, like tick, 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 and you can get an interval from time of this. So it shoots it up, comes back down, and records the time that it takes the light to go up. And these two sides are separated by a distance d. And so the time, we'll call it delta t naught. And what the naught means is time for somebody in the same reference frame as the clock equals this equation, 2d over c. And once again, this is traveling up at the speed of light and then back down at the speed of light, which is represented as c. What this means, how this equals a time interval, is you're basically doing the distance traveled by the light, represented as 2d because it goes up and down, over the velocity, or sorry, in this case, the speed of light, which is in a unit of distance per time. So it'd be over the distance the light traveled over time. And when you multiply that out, you get a distance times, you flip this, a time over a distance cancel, and you just get a unit of time. It'll be a very small unit of time, but a unit of time nonetheless. So this is the concept of a light clock. Basically, it ticks like this, tick, 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 tick. And you get a very small amount of time, but nonetheless an amount of time from that is delta t naught from this clock, and that's how a light clock works. The next thing I want to show you is that velocity. Well, this one I'm going to show you. Okay, in this thought experiment, there's going to be a spacecraft like this. Okay, and this is going to have a time clock on it. Okay. It's going to be moving at a velocity of v. And you're going to have a little person over here standing here watching this spacecraft. And they're going to have their own clock. And the time that passed by for them is going to be delta t. And the time that passed by over here is going to be delta t naught. Let me actually write this on this side. So it's going to be delta t naught. And this is going to show the relationship between delta t and delta t naught. The overall distance that this spaceship travels, that this person perceives, is going to be the velocity times the delta t is going to equal the distance traveled by the spacecraft in a certain interval from this person's reference. That's something that you're going to see a little bit later. And now, a very important concept right here is I'm going to show the spacecraft as it has traveled a certain distance, okay? Light clock, okay? Normally, a light clock, for a person standing next to it, would see this. They would see it bouncing up and down, up and down, up and down. I'm going to slow it down just so you can see it a little bit better. Bouncing up and down, up and down, up and down. But once it starts moving, if this person were to trace the path of that light, they would see this. Up and down, up and down, up and down, up and down. That's what they would see the light path take. Because it's normally bouncing up and down, but once the spacecraft is moving at its velocity v, you would see this. Right? So I'm just going to draw one of these arcs over here. So the light beam bounces up and comes back down. And this is the path of the light that this person over here sees. Okay? In one, of course, one of these intervals. And again, this is you know, a distance d, and the whole distance, let me draw that is traveled by the spacecraft is going to be represented as 2L, just for mathematical purposes, such that half of the distance until it gets to here is going to be L, and the other half is going to be L. Okay? So in this case, we're kind of making a triangle over here with the distance traveled, half the distance traveled, the distance between the top of the clock and the bottom of the clock, and this beam of light, which were the distance traveled by the beam of light over here is going to be denoted by S. So that L squared plus D squared equals S squared, because the triangle L squared plus D squared equals S squared. And this is another little relationship in this scenario. And the last relationship that I want to show you is that this S, the whole path traveled by this beam of light, because it is a beam of light, is going to be represented as, you know, 2S. It's going to equal, because the total distance by the light is S and S, which is 2S, equals the speed of light times delta t. Just like 2L, the whole distance traveled by the spacecraft, is the velocity of the spacecraft times delta t. The S, as seen by this person, 2S, sorry, the total distance, is going to be the speed of light times the change in time. It's another little relationship. And so this is just, that's going to be the end of the video, and this is all setting up for a very interesting, at least I think, thought experiment on time dilation and length contraction and special relativity based off of this.